Okay, so this is very nice. What this tells us now is that we have the expression for the u component of velocity. What's left to be determined, of course, is this dp dx and also the vertical component of velocity v. So before I do anything else, let's call this equation 3. Okay, so now we have dealt with equation 2b. To find the pressure gradient as well as the vertical component of velocity, we have equation 2a. So what we can do is solve equation 2a for v by integrating it out once in y. That will give us v in terms of this pressure gradient. I then have two boundary conditions. One I can use to determine v, because this equation 2a is just first order in v. I have another boundary condition which serves then as a constraint, allowing me to calculate dp dx, which in terms of this scheme is actually another constant of integration after integrating with respect to y, because dp dx, remember, is independent of y. So that's one way of proceeding. However, a more elegant way of doing it, which actually allows us to get the pressure gradient, an equation for the pressure without ever calculating v first, is to use equation 2a to derive an integral equation directly relating the variations in flow rate to the changes in the gap thickness. Again, this is something that we had done in the context of the wavy-wall earlier, and it was also useful in our calculation there. So now we are thinking of proceeding towards calculating the pressure gradient and v, but for that we first stop over to look at an equation for the flow rate, or the integrated u equation. Right, so we begin now for this from the continuity equation, which has dou v by dou x, dou v by dou y now equals minus dou u by dou x. This is my continuity equation, which I am now going to integrate from 0 to h, of course, dy. Okay, so a direct integration here gives me just v at h minus v at the bottom wall 0. And on this side, I'm now going to use Leibniz rule to take the integral out. So I'll get minus, so let's take the minus sign outside first. Right, so if I take out the derivative ddx, the first term is going to be, remember, h is a function of x and time. Right, and then from Leibniz rule, I know that the way you normally write Leibniz rule is the derivative of the integral is equal to the integral of taking the derivative inside plus the derivative of the top limit times u at the top limit, and the same for the bottom limit. But because I have, I'm using the formula in the reverse way, I'm actually going to have minus here the derivative of h with respect to x times u at h, and then plus anything coming from the bottom limit, but here we see that this is now independent of x, so I get nothing surviving from the bottom wall. Right, so this is what I have here. Now some simplification is in order, so I know that v at the bottom wall is 0, but v at the top wall is capital V, right, because I allowed the top wall, although it doesn't move horizontally, it can move vertically. So I'm going to have capital V sitting here is equal to minus now d dx of, now what is this integral? This integral is nothing but the flow rate q, right, and I'll have plus times now u at the top wall. Okay, now u at the top wall typically is 0, right, so I could set this to 0 immediately, but in the more general situation I want to show you that you can get the same formula, the same formula we're about to derive between the flow rate and the gap thickness, even if u at the top wall were non-zero. So to see that, let's set this equation aside for the moment, and let's realize the fact that let's find a way rather to relate the time derivative of the gap thickness associated with variations in the top or bottom wall to the velocity components at the walls. So to see that, let's note that the top wall right, is a material surface. Right, this is trivial because the wall itself is composed of material points, because the wall never moves and the velocity at the wall is zero by, the Lagrangian velocity at the wall is zero because of the no slip condition. So I know that, in other words, points that are at the wall will remain on the wall for all time because they are stuck at the wall. So now if the wall is described by a function f of x comma y given by y minus h of x comma t is equal to 0, this is in fact the relationship describing the top wall, then I know that df dt for all Lagrangian points, material points at the wall, is 0, right, which implies, if I take the partial derivative forward, I have minus dou h dou t coming from the local time derivative, right, plus v at the wall, which is capital V, dou y of this entire function, which is just 1, and then plus u at the wall times of course dou h dou x, and there will be a minus sign sitting right here. So all this must be equal to 0. So this implies that dou h dou t in my case is actually, well, to write it in general, v at the wall minus u at the wall dou h dou x. So this is a general identity that we can derive even if the wall has vertical and horizontal components. So substituting this in the above equation, where you see that v at h is nothing but capital V, and u at h is here. So even if u at h were non-zero, this relationship holds. And if I take this to the other side, you see that you just have dh dt here. So the final result we get is dou h dou t is equal to minus dq dx. Okay, in general, I'm sorry, I should actually write it as the partial derivative of q, because even though it doesn't depend on y, it could very well depend on time. So q could be a function of time, of course. Right. So this is the sort of thin gap equation for the flow rate, right? And so when all thin gap problems, even free surface problems, this is a general relationship that holds regardless of the boundary conditions of the problem, because it just arises from the application of, by integrating the continuity equation and using Leibniz rule. So it's quite general and holds for all thin gap problems. And it's just a consequence of conservation of mass. So it has nothing to do basically with the special nature of the boundary conditions. In fact, if you see, it has nothing to do even with the thin gap approximation, because nowhere did we use the fact that epsilon is small. It's the exact continuity equation integrated gives us the following exact equation. So in fact, I can even remove this thin gap qualifier here and just say it's just a flow rate equation in an integrated form. So a better term might be the integrated flow rate equation relating changes of flow rate in the longitudinal direction to variations in the thickness of the gap. So what this tells us is if the gap has to locally increase in time, it has to do so by accumulation of fluid coming from gradients in the transported flow rate. Okay, so let me call this now equation 4. Alright, so now you see that I can immediately obtain an equation for the pressure gradient, right, by substituting equation 3, using equation 3 to calculate Q, substituting it in equation 4, and then if I know dh dt, as I do in this problem because it's prescribed by the imposed wall movement, I can then obtain a second order differential equation for the pressure. And so I'm able to calculate the pressure directly without ever having to calculate V. Of course, then if I calculate the pressure in that way, I can go back and calculate U and also calculate V by integrating the continuity equation. Alright, so let's proceed to do that. Let's proceed to now obtain an equation for the pressure field. So I know from equation 3 I have that q is nothing but the integral of 0 to h of x comma t. Remember I had g minus dp dx. Where was that? Yes. hy minus y squared, the whole divided by 2, plus u into 1 minus y by h dy. So what's required now is I simply do one integration, which is straightforward because these are just simple polynomial functions, and then apply the limits so that I get the flow rate in terms of dp dx and the thickness of the gap h. Right, so again I leave you to calculate the details, and what you will find is that I'll get q is equal to g minus dp dx into h cube by 12 plus u times h by 2. Yes, this is the expression for the flow rate. As you see, it does make sense, right? The motion of the bottom plate drives a flow due to the bottom plate's velocity, but with a factor that is associated linearly with the gap thickness. On the other hand, pressure variations, both overall imposed as well as induced by variations of the gap thickness, also drive a flow rate, but you then have a factor of h cubed by 12. Right, so you can see the smaller the gap, naturally the smaller will be the flow rate for a given pressure gradient. And so if you want to have the same flow rate, to maintain mass conservation, the pressure gradients have to keep increasing, which is really why, that's why the pressure gets large values, as I mentioned. All right, so this is now my equation for pressure. From here, of course, I can calculate dq dx. So I get dou q dou x from here. So I don't have to write this down directly, actually. Right, so the point is I can calculate the gradient of pressure directly, substituted into 4 now, which is just the integrated flow rate conservation equation, integrated mass conservation equation. And that would then give me an equation for pressure. Right, so let's write that down. Again, take a second and work it out for yourself. So remember, it's minus dq dx is equal to dh dt. Or actually, it may be nicer for me to Yes, that looks right. Right, so what I've done is just written minus dq dx is equal to dou h dou t. So I get minus u by 2 dh dx, which I've taken to the other side, and of course this term survives. So this g now is just a constant. So because of this nested integration form, I can do one integration and then take g to the other side and perform the final integration on pressure. So it's nice to write it in this form. But now we can replace in general the fact that dh dt being known is just v, right? So my final equation for the pressure looks something like this. Right, where g is now a constant, right, is always a constant, is equal to v, right, this is just v plus u by 2 h to x. Great. So there you have it. This is my second order differential equation for the pressure. Of course, this is the scale pressure. Remember, the pressure is order 1 by epsilon times the other quantities, the order 1 quantities. Alright, so this is a nice result. This is in fact the lubrication pressure equation for problems, of course, where you know where the motion of the walls is prescribed. In a free surface problem, the evolution of h is actually an unknown. So in this case, this equation would actually be an evolution equation that allows us to determine in capital H. If we calculate, and the pressure gradients would have to be determined simultaneously that way. But here this gives us an equation directly for the pressure. So this is an equation that I can solve now, provided of course I have two boundary conditions on pressure. Once I can solve for the pressure field everywhere in the domain, I can go back and calculate u. In fact, I know u in terms of dp dx. And I can then go to my continued equation and integrate it out in the domain to find v at all points. So that basically by solving this equation for pressure, I get not only the pressure field, but also the u and v components of velocity at every point inside my flow domain. So really the last step is to solve this problem, and for that I need to impose, like I said, two boundary conditions on pressure. So to understand what boundary conditions have to be imposed, it's again helpful now to think of the two different classes of problems that we have, right? One is the problem, one is the problem associated with regular perturbation scenarios. For example, flow in a wavy-wall channel. So in that case, the pressure boundary condition should just be the inlet and outlet pressures in my domain. But since this P now is a disturbance or deviation pressure from the implied pressure gradient capital G, this small p should just be 0 at the inlet and outlet, because that's where I fix the imposed values of pressure to in fact give me capital G, right? So for flow in a channel with imposed pressure gradient G, I just have P at the inlet, let's say 0 is equal to P at the outlet. So now it could be 1 if the entire length of my channel was used as a length scale. If instead capital L, the length scale was just maybe the wavelength of the waves of the surface or some other suitable horizontal length scale, then maybe this would be lambda, which is some multiple of that capital L, right? So it's some non-dimensional multiple of capital L, such that lambda capital L is the total dimensional length of my channel. So both these pressures are equal and equal to 0. So with these 0 boundary conditions applied here, I can calculate the distribution of the disturbance pressure, which is the disturbance, of course, from the imposed pressure gradient G. So this is for flow in a channel and such related problems, where the entire problem is the thin gap region. On the other hand, for inner layers, right? For inner thin gap regions, right, what are the pressure boundary conditions? Well, For that we need to inquire into the nature of the pressure and flow in the outer region. So for this it would require us to scale the outer equations and then see basically in general it may seem like we would have to solve those outer equations to calculate the pressure field in the outside region and then match the pressure in the inner zone to the pressure in the outer zone. But it turns out that the problem is greatly simplified by the fact that the pressure inside the thin film region is an order of magnitude larger than the pressure anywhere in the outer region. To see that, we look at the 2D Navies-Stokes in the outer region in their scaled form, but it turns out that those equations would be simply the equations we had earlier. Right? If we go back here, the outer zone equations are exactly equation 1, except for the fact that we would set epsilon here would be equal to 1 everywhere, right? Because in the outer region there is no length scale disparity. The length scales in the y direction and the length scales in the x direction will have the same order of magnitude in the outer region by definition. So you would get the same same scaled equations, except that epsilon would be set to 1 everywhere, except for the pressure terms. Right? In the two pressure terms, this epsilon would be set to 1, but because the pressure scale still has 1 by epsilon, I would get a 1 by epsilon and 1 by epsilon multiplying both the pressure gradient terms, and everywhere else epsilon would be set equal to 1. Right? You can convince yourself by going back and looking at the scaling, but it's quite simple just from the fact that if we use the length scale variations here instead of using the h by lc associated with the inner region, in the outer region, let's say you have only length scales of order L. So if epsilon is L by L everywhere here, we would get equations without epsilon appearing anywhere, except for the fact that the pressure scale would still have this behavior which you would have h by L. So the consequence is that for the inner region, we know that the outer equations at leading order are simply dou p by dou x equal to 0 and dou p by dou y equal to 0, where x characteristic is y characteristic is, let's say, the large length scale L. Right? But p characteristic still goes as order 1 by epsilon. Right? Which is why you have 1 by epsilon in front of the pressure gradients, you multiply throughout by that epsilon, and if you set epsilon to 0, you only get these equations. So what this means is that the pressure in the outer region, the pressure gradients rather in the outer region is approximately 0, and therefore the pressure in the outer region everywhere is really equal to the pressure in the inner region at the boundaries. Right? So, and this I can set to be some reference pressure. So what this tells me really is that the pressure in the outer region is basically unaffected by the flow in the outer region. Rather, the pressure in the outer region is really set by the much larger pressures that are developed inside the thin gap region. And so the outer constant pressure I can set to be some reference pressure, which I can take in general to be 0. And so therefore the boundary conditions then for the inner region on pressure are once again that P at 0 is equal to P at the end of the thin gap region is equal to 0. So you see that I can impose boundary conditions on my thin gap lubrication pressure equation without inquiring into the solution of the outer region flow, even in cases where the problem is singular and the thin gap occupies only a part of the domain. And so now basically I have P equal to 0 at both ends as suitable boundary conditions for this pressure equation, and therefore for a given situation I can solve this pressure equation and obtain the pressure field, and from there I can go back and calculate the velocity field as well as the velocity field both in u and v. So that brings us to an end to the general theory of the thin gap approximation, where you see the theory really boils down in simple terms to having the horizontal velocity field being of a form that is really a local Poiseuille or Couette flow, depending on whether the flow is driven by motion of the walls or by applied pressure gradients. So I have what is really a locally unidirectional fully developed flow expression being used for U, but where the boundaries H are really varying in space. That expression for U in terms of the as yet unknown pressure gradient is used in my integrated flow rate condition, which is which is always valid. It's an exact equation, So by substituting that expression for U here, the assumption of locally unidirectional horizontal velocity into this relationship, I get an equation for the pressure gradient, provided I know how the the gap varies in time and in space in general if I had a moving upper wall. So if those factors are known, as they are typically in these type of lubrication problems, then I get an equation only for the unknown pressure, which is the ordinary differential equation, and the two boundary conditions for this equation are known and can be set to 0 regardless of whether it's flow in a channel, which is a regular perturbation problem, or if it's flow let's say beneath a sedimenting cylinder, which is actually a singular problem, but where once again we can say that the pressure in the inner regions must reach the constant outer reference pressure at the ends of the thin gap region, which is what this condition says.